Good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and I'm the famous interim director of NITheCS. You need to tell yourself something positive every now and then. Yeah. So and I also need to welcome not only you, but also the more than 100 people that are watching online. Sorry, I'm watching them there, but I think they see me in that direction. Sorry. So it is my really big pleasure to introduce you to Ulrich Paquet. Ulrich just moved back to South Africa recently at the beginning of the year, and he's now the director of AIMS, the African Institute of Mathematical Sciences in Muizenberg, and the previous director is also here. So welcome, Barry. Thank you for joining us this evening. Yeah. Ulrich studied machine learning in Cambridge and did his PhD there. And then hopped from many different jobs, from Microsoft to Apple to DeepMind. Yeah, some of you might know that he was on the team that launched the Xbox. So maybe you are playing with his gadgets every day. Yeah, so he's the man. Yeah, and today he will give us a very interesting talk on the history and relationship between AI and chess. So Ulrich, thank you so much for being here this afternoon, and we are all very much looking forward to your presentation. Thank you.
Thank you. Thank you, everyone. So I thought I'd speak to you about two things I'm very passionate about in life. One is chess, which is more like a childhood hobby, and maybe too many hours spent as a teenager. And then machine learning and artificial intelligence. And these two disciplines have interacted and have been friends for many decades. Is the sound okay at the back? Everyone, great. Okay. And I'll talk to you about the history of chess and artificial intelligence and speak to you a little bit about what the future will hold for these two things. And the talk's very much a AlphaZero DeepMind slanted talk, if that's okay. So the first part is just about chess and AlphaZero as a chess engine and what it is and how it came about. Chess is an ancient game. Here is an image from the 1200s. It shows two Spanish medieval noblemen, which we can't see for some reason. Let's go again. There we go. There are two Spanish medieval noblemen in the 1200s playing chess already. And my first experience with AI and chess didn't look at all like these Spanish gentlemen. It was in the mid-90s. It was a Kasparov advanced chess trainer. It was entirely symbolic in the way it worked. It had 8 levels. And it worked on principles that were developed in the 1940s, 50s, and 60s. This thing in the 90s was magical for someone who grew up here in South Africa. And then as a high school student, this event happened. It was the Garry Kasparov against IBM Deep Blue match in New York. This was in 96 and 97. And the picture is gone. There we go. This was the first time that a chess world champion was defeated in a timed multi-game match. And I remember sitting in my home in Mpumalanga, wishing that I could have been in that audience in New York, witnessing that momentous occasion. So Deep Blue convincingly beat Garry Kasparov. It was for IBM, it was really a feat of incredible engineering in terms of hardware to let this happen. And chess has always been what I call a petri dish for artificial intelligence. So many techniques that we know in AI were first developed in silico, in hardware, with chess as a substrate. And from the 1940s, 50s, and 60s, the initial ideas of artificial intelligence all grew out of chess. And I'll take you through a few ideas and ideals. I'll take you back to the year 1770. in Imperial Europe. I'll talk about mechanical Turk in a little bit. And then the next key date in the development of computing as an industry and discipline and as chess was a seminal paper by Claude Shannon. It was called Programming a Computer for Playing Chess. And I'll just read the abstract for you. It says, this paper is concerned with the problem of constructing a computing routine or program for a general purpose computer, which will enable it to play chess. Although perhaps of no practical importance, the question is of theoretical interest, and it is hoped that a satisfactory solution to this problem will act as a wedge in attacking some problems that are other and of similar nature and of greater significance, and then some possibilities in the direction are. And in 1949 already, Claude Shannon, in that seminal paper, described a minimax search, the kind of search that you do in multiple layers as you search for a good move to do as a chess player on a computer. In 1949, he already described the idea of an evaluation function that would be deployed in this minimax search to find a very good chess move. Rolling forward, many things happened, and then 1997 was, of course, the big game between Kasparov and IBM's Deep Blue. And in the late 90s, I was a student in Pretoria, and we discussed the future of AI and chess and games. And it was thought that the Chinese game of Go, that's really exponentially more complicated in terms of its branching factor than chess, would be the last game to fall. And we thought that this would probably never happen. If it does happen, it might happen in 50 to 100 years' time. And lo and behold, it wasn't much long afterwards. It was a good 20 years later. Go was essentially a solved game. And there's the famous game between AlphaZero and Lee Sedol in South Korea that I could talk about in a little bit later if you're interested. So anyway, AlphaZero, which is a precursor of AlphaZero that I'll talk to you about, is a neural network-based Go playing engine. It wasn't self-taught like AlphaZero is, but it used a great amount of data, and it defeated the strongest, probably the strongest Go player in history, Lee Sedol, in a match in South Korea. And that really changed the way people think about things. But if I take you back to, before I go back to the 70s, who of you have seen this movie, AlphaGo, the movie? Here's a fun fact for you. We screened it in the cinema 5 years ago for 5 nights in a row. Are any of you in this audience who were present 5 years ago and watched it on this cinema screen? Okay. So do watch that. 1770, Wolfgang von Kempelen, Austrian man, devised this machine. It's called the mechanical Turk. It was a puppet that could play chess. This machine toured the imperial courts of Europe and beyond. It was a phenomenon at its time. It was really an artificial intelligence agent because there was a human hand in the loop. And this is roughly how it worked. You had this crazy machine, which was a big table, and a very, very tiny person, a very good chess player, would hide inside. And with a very careful constellation of mirrors, this person could be hidden so that you'd open any door, and then the person would silently slide to another side of this box, and you'd never know that there's really a person inside the box. From any angle, it would look like the box is completely empty inside. It was quite a strong chess player. And what do these two men have in common? We have Benjamin Franklin from the US and Napoleon Bonaparte. Both of them lost against the mechanical Turk, this first chess playing agent, or AI. Okay. In the Alan Turing archives, there are some very interesting comments on the development of chess. And I'll read a few sentences to you from a paper that he wrote called Faster Than Thought. This was in 1953. There are some really fun things in here. So Alan Turing wrote a paper, and he said, can you make a machine that could play chess? We know the answer is yes. And then I'm going to zoom down a few bullet points and get to his point number 4. Now, this is 1953, post-war. And Alan Turing said then, could you make a machine to play chess? And to improve its play, game by game, profiting from its own experience. This is an allusion to a machine that would teach itself how to play chess and learn to improve its play from its own mistakes. And then he asked a few more questions beyond this. He said, if you can see that, he said, could you make a machine which would answer questions when put to it in such a way that it would not be possible to distinguish its answers from those of a man? And that question, if you're familiar with the history of artificial intelligence, that is what's called the Turing test. And there's the Turing test on a very faded piece of paper typed out for the first time. And then lastly, could you make a machine which would have feelings like you and I do? So here are Alan Turing's thoughts. He says, well, to questions 4 and 5, I should answer, I believe so. So I have no really convincing argument why I should support this belief, but I do think it's possible. And then to his last question, could you make a machine which would have feelings like you and I do? Alan Turing said, I would say I shall never really know any more than I shall ever quite be certain that you feel the same way as I do. So AlphaZero as a chess playing engine is very different from a traditional chess playing engine. And I'll show you a few similarities on how Alan Turing's prediction became true a few years ago. So a traditional chess engine is built by what I would call the craft of handcrafting. It means that you would, as a chess player or as an engineer, devise a set of handcrafted rules that you would encode to evaluate any chess position. You would then do some manual feature extraction. So you look at the chess position, you count the number of pieces, and you devise some rudimentary scoring function that could be used and employed. If we want to move to a self-taught system, all of these things have to be replaced with a system that can learn itself, that can search in some way and look ahead, and then has a mechanism for self-improvement. And these will go in a loop. If you are interested in buying a really nice birthday present book or a Christmas present book, there's a book called Game Changer by Natasha Reagan and Matthew Sadler, which describes a bit of some of the more interesting AlphaZero games. Okay, there is a difference between how people approach a chess position. A top chess engine like Stockfish would evaluate millions of positions in order to make one move. A top human grandmaster, a really, really good one, would evaluate a few hundred positions for a really complicated position. And then halfway on this logarithmic spectrum sits AlphaZero, which would evaluate roughly 10,000 positions before it makes a very good move. And there is a research challenge in here in terms of the future of AI and chess, and that is that we used to increasingly rely on computational power to devise very intelligent agents, and these are very power hungry. Each of you who sit in this audience can make very intelligent predictions just by the power of eating a banana. You're very low powered, you're very slow, your brains, and it's extremely distributed. And in terms of the future of research, it would be great if this the spectrum could be moved and we find computational paradigms that would work in the order of hundreds of moves in terms of evaluation. And see if we could do that very well. Okay, so any self-improving learning system would have these 4 things that would run in a loop when you train and improve it. It would have a component that could learn. It would have some component that could make decisions and act on the world. It would then experience a different or changed world, and then that would lead to some improved data. So this is the typical reinforcement learning loop. Inside the mechanics of AlphaZero, the learning system looks like this. So you'd start with a large volume of data, which are chess games. The data don't have to be good games. In fact, they could be games that you play against yourself as a complete beginner or idiot that barely knows the rules of chess. And every game has a sequence of states. I call the state S. And the state leads to an ultimate game outcome, whether you win the game, whether you lose the game, or whether you draw the game. So this would exist as a big corpus of data that you could use. So from this position, I would know that in this game, someone probably won the game, white. So the indicator Z would just be a 1 for white. The second kind of, just before I get to that, so we would build a neural network that would predict the ultimate game outcome from the position. So here we go. So we would try and estimate the value of the position if I follow the best policy that I have at the moment, if I play according to my current neural network and best search. And that neural network would take as input the chess board or the current position, and it would emit or predict the expected game outcome from lots of data given that board state. So we want some neural network that could generalize. From data, we also have another component that we could use or utilize, and that is that every move in a chess game leads to another state. So in a state, you make a move which is an action, and that leads to another state, and it's entirely deterministic. So the second neural network would be some neural network that predicts which moves could be made inside from a position, and which moves are good moves. So this state S could lead to any one of these next states, given any action that you've played. So we could replace that with a neural network that we call a policy network. The policy network just says which actions you could potentially make in a position, and it would be like a recommender for getting a short list of moves to evaluate. So we learn this from data. If, of course, your data set is a beginner's data set, these two networks would essentially emit junk. And using these two neural networks, we let AlphaZero or some system play against itself. So you play again against yourself, and you use some search to make decisions. Very briefly, the search is done with Monte Carlo tree search. It uses a neural network to expand a sequence of moves, evaluate how good the sequence of moves is, roll it up to some score, and repeat it over and over again. I'll tell you the details about this in a little bit later. And this would be done over and over again with a special formula that trades off two things in reinforcement learning: the idea of exploration and the idea of exploitation. So exploration just means that you really want to make sure that there's not something amazing happening that you didn't try. You really want to try everything. Exploitation means that you want to find the thing that's really great, and you want to do that over and over again. And there are many theoretical bases for how you do this mathematically. So you want to trade off two things. You want to trade off how quickly you explore unknown moves and options in case there's something great that you've missed. And at the same time, you also want to try things over and over again that you think is going to give you a great payoff. So you want to explore the lines that are potentially better. So of course, then you pick a move that you've explored a lot, and then you make that move, and that leads to a changed world. And the changed world means that you have improved data. So if you have a neural network that makes fairly stupid moves, and you combine that with search, which would detect checkmates, etc., then the resulting data set, if you do it well, would be a tad better than the one you started with. Make sense? This dumb neural network plus search equals slightly better data. And this process and this loop is then repeated over and over and over again with a few hyperparameter settings to make it balance out and learn. And so eventually you end up with a system that is trained with zero human supervision and input. It discovers and reweighs the way people play chess. It reweighs certain themes, and it's superhuman. Okay. So here are the two parts. And for people who are really into neural networks, I thought I'd just show you what the architecture looks like. So we've got two neural networks, a value network and a policy network. If you were to implement this yourself, you'd probably try something like this. Over many rounds, this works very well. It's a 20-layer, 20-block residual network. A ResNet is a very simple neural network structure where previous information is essentially copied and appended, copied and adjusted according in a long stack. So you have 20 layers of fairly complicated computation stacked on top of each other. And at the top layer, you split into a part that makes the next move prediction and a part that evaluates a chess position. It's not really important to know what the internals of this thing are, except that you have a composite function that does a computation in many layers. And what I'm going to tell you a bit later is how that computation is very human-like. It's surprisingly human-like. Okay, this is how decision-making works, just for people who are interested in coding it at home. A bit of math. This is the only math you'll see in this entire talk. So you've got a state. You have a neural network that predicts as a probability which move to expand next. This probability is slapped into a formula which looks like this. It has an action value part. The action value part just says, from a specific state, how good is a move or action in a certain position? And this will be refined in search. It has a second part, which is the U term, and this is used for exploring. So we'll try and trade off these two things. So I run this formula over all possible actions, and then I pick the action that maximizes some score, and that's the one that I expand. And I expand that action, so I make the move, and I repeat this process over and over and over again until I reach a certain depth. Once I hit a certain depth, let's say 20 moves or 20 plies a look ahead, I stop. And then I evaluate the position. And I get a value that is eventually propagated up. So I employ a second neural network at the leaf node of this search branch. At the leaf node, I would evaluate and I would propagate this Monte Carlo estimate up. So I would essentially compute a value estimate for every node in this search branch of this Monte Carlo search tree. So my action value estimate just increases. The number of times a branch in this tree has been visited, that increases, and the total value increases as well. So this goes one level up, then another level up, and then all the way to the root. And that is one Monte Carlo tree search simulation. It goes down, then it goes all the way up again to the root. And I would repeat this probably 10,000 times over for a very good engine. And after one MCTS simulation, I'd repeat it. I'll skip the formula here. You can read that in a paper. And eventually, what I end up with is a branch that was visited more times than any other branch as a next action. And that is the move that I'll play as a chess engine. So that is decision making for you. Then I am, if you're familiar with a literature called the multi-arm bandit literature, this is got to do with slot machines and gambling, and you want to pick the slot machine that gives you the highest payoff. This move is like the slot machine that you pull. You get the highest payoff. This direct mapping between these two. Okay, so we've got this self-adaptive, self-improving learning system, which is learning, decision-making, changing the world, and some improved data to it. But that leads me to artificial general intelligence, which is a much more nuanced challenge than chess. In chess, everything in the world is fully observed. Nothing is hidden. There's no partially observed state. And if I were to give a talk and my goal is to give a good talk, many things are hidden. I don't know what's going on in your heads. I don't know what your intentions are. I get partial feedback. Some people nod and say, yeah, you're doing great. Other people might leave the back room. So I, as an AI agent, need to do a lot of inference to fill in what this partially, the unobserved state of the world is. So chess solves the fully observed part of reinforcement learning and decision making and planning, but it's a tiny, tiny part of a much, much, much bigger research story. So the world is just so much more nuanced. So this is a tiny step. What concepts does AlphaZero learn? For me, this was the most exciting research development in my personal life in the last 2 years. If we were to let a superhuman self-learning AI agent loose to train itself at the superhuman level, would it ever learn human-like concepts? And would it discover a curriculum that is a bit like the curriculums that some beginner chess player would follow? Does it learn any concepts that we could recognize even? And when does AlphaZero learn those concepts? And is it at all like we'd expect? So here's one way to approach the problem. So many engineers have built chess engines that have evaluation functions that are a composition of different concepts that a chess player might care about. So if you were a Stockfish designer or someone who codes the Kasparov chess engine that I played with as a high school kid, then you would look at the composition of pieces on a board, the mobility, you'd count the pieces, you'd see whether there's a pawn that's close to the last rank that could become a queen. You would look at castling rights, you would look at a large number of concepts that you could describe with a human vocabulary. So if we have access to a system that gives us those automated labels, we can detect whether that data exists or is detectable in a big neural network. So here we go. So from a position like this one on the screen, a chess engine would tell me something about the material difference. It would tell me about its total score, how it evaluates the position. It would tell me about, it would give a numeric value for whether white pieces are threatening the black pieces and vice versa. And we can get a large number of automatic labels from a position. And then we want to know whether any of these concepts are present in any of these layers of this very, very deep neural network. So we can hypothesize that as a human, when you play chess, you would look at the chessboard, and at the first layer of visual perception, you would recognize the pieces on the board. And then you'd recognize some basic patterns and constellations between pieces. And then some higher level processing has to happen that will allow you to make a decision. And finally, when you make a move, something has to happen that takes the decision and moves it to actuation. So let's see if the same thing happens in AlphaZero. So we'd hope to find in the first blocks some detectable pattern recognizers, and then in the middle blocks maybe something more complicated. And so we'll take a block like block 10 in this really big neural network, and we'd compare that block to some function that we code, like the Stockfish's total score, and then measure the linear correlation between what's encoded in that layer and then the output by a different engine like Stockfish. So I put thousands of chessboards through the network. I'd measure what's happening in layer 10, and then I'd measure Stockfish's score and see whether there's any linear correlation between these two. And then for a block, which is the block axis, at some point in the training process, I would get a measurement of correlation, or R squared. And then I would do this for all layers in the neural network. So for instance, if this is the total score, the total score function by Stockfish, you'd find an increase in correlation as you progress through the different layers of your neural network up to a certain point. And we do this over and over again for many rounds of training, AlphaZero. So what you see in this picture is that as the network is initialized at training step 0 on the logarithmic scale, absolutely nothing is encoded. And as the rounds of self-training progress, this neural network is updated and it's improved. And improvement happens for up to 100,000 or so iterations. And then there's a peak where AlphaZero as a chess engine is maximally correlated with the total score that some other chess engine like Stockfish would give. And as training progresses, there is then a slight divergence as the one engine becomes better while the other one remains static. And you'd also see that at the very end, maybe you can't see it so well for total score, but there's a slight downward slope. Okay, so we could do this for other things as well. So we could look at the material value of a position. And if I look at total score and the material value, you see that material is picked up very, very early on as a concept that is learned. And material value is concept that is learned and that is used in the intermediate layers, like layer 10 out of a 20-layer residual network, and then is slowly discarded because it's a kind of information that you need to make a prediction, but it's not the information that you need to make a final prediction. It's information that you're going to combine to make later predictions. So here are a few high-level concepts. So the most interesting one is how threats are viewed. So you can't really see it that well on the slides, but as AlphaZero becomes better, its view of threats also starts differing from Stockfish's. So we call these things what, when, where plots in terms of explainable AI. What concept is learned? Where is it learned in the neural network? And when is it learned? When does it arise? There are a few others. The most interesting one here is a concept called imbalance. So because AlphaZero is self-taught, it really tends not to care about material imbalance that much. So whether you're a pawn behind or a piece behind or a knight behind, if you have some other property of the position that would give you a significant advantage. So for threats, for instance, you really see that there's a strong downward tail. Okay, there are other interesting things that you can see from analysis like these. So AlphaZero and Stockfish's evaluation doesn't have to be the same. So to explain how a chess engine works is you would, if you were to do a forward roll in a traditional chess engine, you'd make a few moves, and then if a position is unresolved, a classical chess engine would continue expanding the moves until the position is resolved. So for instance, if I'm halfway through exchanging pieces, a traditional chess engine would continue evaluating the position until the coast is clear a little bit. AlphaZero does not have that luxury. So it would run Monte Carlo tree search up to, let's say, 20 moves in depth. And at that point, whatever your evaluation is your evaluation. So if you are halfway through exchange of queens, which are the most important pieces, a traditional chess engine would tell you that you're far behind in pieces. AlphaZero would tell you that everything's okay because you can just capture it back. The position is equal or even. So if we look at the largest residuals, in that when the predictions of AlphaZero are least correlated with those of Stockfish, and you actually dig into what these errors are between the two engines, then under the hoods, you always find the largest errors being places where stockfish values a queen exchange differently than AlphaZero. And it shows you something about the nature of these two different chess engines. Okay. The next part, Francisco, how much time do I have left? 15 minutes. Okay, then we have a lot to do. Okay, would a self-taught AI acquire skills in the same order that a human does? So a self-taught AI, so if you were to learn to run, you would first learn to crawl, and then you'd learn how to walk, and then you'd learn how to run. So in the chess world, is there any analogy to crawling and walking and running? So if you're a chess player, you would probably start and you would learn the pieces, the value that people traditionally assign to pieces. 1 point for a pawn, 9 points for a queen. And then you'd read a book about the basics of chess. And then maybe at some point you'd read a book which is like how to think like a grandmaster, more complicated concepts. And then eventually you're like a world champion, like Magnus Carlsen over there. But there is a very set curriculum by which a human would become a very, very strong chess player. Some things you need to master before you can master other things. So does AlphaZero do the same? So I'll give you a few glimpses. One is in generating candidate moves. I'll just show you the question here is how AlphaZero's first move differs from the way humans make their first move. So this is 500 years of human discovery in chess. If you are chess players who know something about chess. Okay, so we'll start in the late 1400s. In the late 1400s, and this is from a lot of chess-based data. It's from 8 million chess-based games. In the late 1400s, people moved the pawn in front of their king, and that's the only thing they did, really. And then in the 1930s, there was this school called this hypermodern school, and people started to move the pawn in front of the queen. And you see this fashion evolved, but you see the fashion evolve from a single move that people thought in medieval times was a good move. This is 1 million iterations of AlphaZero discovery. Unlike our medieval knights, AlphaZero tries every possible move in the book. And then from every move, it essentially drops the probability for the ones that don't work. And it slowly converges to a policy where the main moves that we know in theory are good moves are being played. So it seems like human history started with a single option and then expand, and that's knowledge. AlphaZero started with every option in the planet and then narrows it down, which is a very, very different way of learning an advanced strategy. How are pieces evaluated in a chess position? I'll quickly show you how we can get to piece values. So we have a value network, a neural network, and it gives a number as to whether someone's winning, losing, or drawing. And we want to know whether that can be broken down into 1 point for a pawn and 3 points for a knight, etc. So if you're a physicist, you probably like this idea of like perturbations of first and second or third order things. So at your first order, when you evaluate a chess piece or a chess position, you just count the pieces. And then the more complicated stuff comes after that. So here's one way to do it. You have a very simple network. This is where the torso in this case is this big 20-layer stack, and you have some input. And we would, you can take for any input, you can take a small function that would tell you what the concepts in that input is. So it's something you can hand design. So for instance, these concepts would say, okay, you have 1 queen, you have 2, the next one would be, you have got 2 pawns and the opponent has 3 pawns. So you're like -1 for the pawns. You have 1 bishop, your own opponent has 2 bishops. So you're -1 on bishops. And that gives you a little vector. And from those features, all you care about is whether from the features you can extract that have something to do with piece difference, whether you can find a weighted combination that would predict your ultimate score. Okay, and this is what you get from this linear regressor. If you start training, like any beginner, you really like your queen. And then as training progresses, the relative values of pieces go up and down. At some point, it really likes pawns. There's some uncertainty as well. And then as the engine becomes better, it starts converging to something you can actually distill from the neural network with data. And it's remarkably, it goes 1, 3, 3, 5, 9, just over 9. Which I find absolutely fascinating. I don't want to call it a scientific discovery because I learned it when I was 6, but for a neural network to teach itself how to play chess and then to have a mechanism to discover this information inside a neural network that you knew as a 6-year-old, I think that's pretty cool. Okay, and you can do this for more advanced things as well. So we can take other concepts of material, king safety, mobility, and I'll just quickly run through these. So as a beginner, AlphaZero likes material, like any other beginner does. And then it starts thinking about threats, but material is still important. So these are the relative values that AlphaZero would put on different human-like concepts when it evaluates a position. Material is still important, and then eventually it has a way of combining human-like concepts where it says, I like material, but king safety is also important, etc., etc. And the order of this is really interesting because if you run back in time, it has no concept of threats and the implication of threats. But as a beginner, it already knows about material, and it seems like there is a sequential order by which these things have their inflection points. Okay, so there is a bit of a curriculum that's happening here where you learn about material, then you learn about basic openings, then threats, then king safety, and this is entirely self-discovered. I want to skip this and just mention a few last things. You can do unsupervised concept discovery as well. So we know that in AlphaZero there are there's an encoding of concepts that are beyond any human understanding or comprehension, and there must be because it plays at a rating that's almost 1,000 ELO above the top grandmasters. I'll show you a few pictures of things you can get from other tools and techniques. Doesn't matter what the tools are. Here's non-negative matrix factorization. All it does is it tries to distill or it tries to factorize AlphaZero's representation into concepts that a human could possibly try to label or attempt to label. So you could see bishops moving sideways, etc. in here. Francesca, will you give me the 5-minute warning? If there's no 5-minute warning, I'll speak to you about the Jennifer Aniston neuron. In neuroscience, there was this old idea of a Jennifer Aniston neuron, which was neurons in your brain that fire specifically when you detect a certain person's face. And we see these things in AlphaZero as well. So we can, for any neuron in any of these, so there's 20 layers, but every layer has a few internal layers. For every unit in these layers, we could correlate the firing of this unit with all pieces and constellations on the input board. And that correlation will tell us how the unit's activation correlates with features, stuff on a chessboard. And skipping the math, something very interesting is that you see two things happening. So this is a neuron or unit, and it sits in layer 20. So this is a layer that's very much at the top of the AlphaZero computational stack. And at layer 20, it still fires when there are two opposing pawns present at the input. And it doesn't look at any other pieces at all. So you could find very, very, very basic patterns in the later layers of the network, and you can find these Jennifer Aniston-like units or neurons that only look at very specific things in your input. And of course, this is easy to do because you have an 8x8 chessboard. So this computing this these correlation matrices won't break the bank like it would for images and other things. Okay, there's a paper that you can read in PNAS if you're interested on how this works. Okay, and then the last thing I want to talk about, and Francisco, you need to stop me if I'm going over time, is reimagining chess. So chess at the highest level is an extremely drawn game. People are experimenting with different time controls to spice it up a little bit. But a top grandmaster would go to a world championship match armed with, I want to say, terabytes of computer preparation. And so you'd often find games where people get into the 20th and 30th move and they're still in their home preparation. So there's not a lot of creativity that's happening on the board anymore. And some former world champions have really expressed the desire to make chess more creative and actually put the fight on the board and not at the computer at home. One of them is Vladimir Kramnik. So I've had a few collaborations with him. He's now a retired world champion, and he had a few ideas. Actually, I should maybe tell a different story first. How the explainable AI work came about was Vladimir Kramnik visited us in DeepMind three pre-COVID, so long ago. And he spent a few days with AlphaZero and put a position on the chessboard that the Russian Olympiad team analyzed for many years, something like 10 years. If you're a chess player, it was from the Berlin defense. It's very early move. And we turned off Monte Carlo research, so it is just the neural network. And Vladimir put the position on the board and said, what does AlphaZero play? And within a fraction of a millisecond, AlphaZero made the Russian Olympiad team's move. And so Vladimir Kramnik says, okay, gentlemen, what's going on here? Why does AlphaZero make this move? Why does it make this superhuman move? Why does it not? What does it know that we don't know? And we had to say, sir, we're really sorry. We have absolutely no idea. And hence this work on explainable AI and trying to find out what the interesting things are that we could learn from a superhuman chess engine and extracting knowledge from it. And everything we've given to Vladimir Kramnik, he says, is yes, explanation we would give to a 5-year-old, not to a world champion. But at least we're giving explanations to 5-year-olds. But his other idea was to change the rules of chess a little bit. And one of the changes for the rules of chess was to remove the castling move. So if you're a chess player, or if you're not a chess player, castling is a move you make in chess. We essentially swap two pieces. You swap the rook, or your castle, and your king. And it's the only move in chess where you move two pieces at the same time. And it's very medieval because the king had to hide behind his troops and his castle, and he had to be hidden somewhere safely in the corner. And so it's not a natural move in chess. So Kramnik had this idea of removing castling altogether in chess. And there are a few other big chess players who also proposed this idea in the 90s, etc. 1990s. And if you want to implement the rule change at world championship level, it's pretty hard to predict what how chess would look like, what chess would look like. We don't have the luxury of 500 years of evolving chess and seeing what the openings are going to be and whether the game is more drawn. So the proposal was to do all of this on a computer with AlphaZero. It's extremely simple. We take the AlphaZero system as it is, and we make small rule changes. So we say, AlphaZero, you're now not allowed to castle anymore. And we let it train. And then eventually at superhuman level, we stop and we collect a large collection of games and analyze these and see if this is actually interesting. And then you analyze statistics of the engines. There are a few games that, so these are all what-if questions. There's some atomic rule changes. I won't go through everything that we did. That will be quite dull. And you could just go online and read it. But there's some important bits. And what is the important bit? Well, the most important thing here is that AlphaZero showed that it finds Vladimir Kramnik's favorite opening from the 2000s, and that's its discovery. But you could also see that that here's a good one. That some versions of chess are more decisive and some become more boring. So in this graph, with this plot, I show you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 different, do I count? 11-ish different versions of chess. And each version has a slight perturbation to the original rules. For instance, you can move a pawn only 1 square at a time, or you can't castle, or you can move a pawn 2 squares every time, really to make it fast and furious. Or you can capture your own pieces, because sometimes you just want to get a piece out of the way and it's your own pieces, so you just self-sacrifice by capturing a piece. So there's this one where, which is a big question from the 90s, is whether stalemate, when someone's not checkmated but the king can't move, whether that shouldn't count as a win. And then with analysis like this, you can actually get a good grasp of which chess versions would be more exciting or less exciting, and you can analyze the number of possibilities that the player would have. I'll skip all of this. We can talk about this in length. There's a fun article with a video in a journal called ACM Communications. It's called Reimagining Chess with AlphaZero, and this gives the outline of the analysis. And if you go online and you're really keen on actually walking through games that are a bit weird and strange, these are all on archive. If you search for chess commentators like Ulrich Paquet, you'd find games that are analyzed and really discussed that are some of these weird and wonderful games as well. So I think I'll conclude there. I don't have a watch, so I don't know when to stop. But the future story is that AI and chess have always lived together since the 1940s. Chess was the first AI application. It's currently solved. The challenge now is to know when we've actually plateaued and built a chess engine that can't ever in history be improved. That is a very difficult question, because it's virtually impossible to come up with a theoretical proof of optimality. So everything is just done as one chess engine competing against another. But so that strand of research is, I think we've reached the end of that strand of research. But there's another extremely interesting strand of research, and that is to, again, use it as this petri dish to experiment and see what techniques in explainable AI we could build and construct from chess, which we understand as a game, and a game that is fully observed, like this crazy world we live in. Thanks.
Yeah, thank you very much for a great talk. Thank you very much, Ulrich. Then I would